it works. So good evening. Yeah, we have a problem with the Wi-Fi today, but apparently it works with my portable Wi-Fi. Let me remind you what we have done last week, and I will quickly finish this chapter, and then we move to something else. So I have introduced, we are just discussing some forecasting method, and I introduced two very quickly. One is the simplest one with polynomial, and then one with linear combination with training set. If you have enough data, you can use this data for forecasting the future data. These two are not based on any model for the evolution, but it's a kind of model about the data themselves. And I have introduced also the method of least square, which is just to minimize a quantity, which is a norm square. Now, if you have a model for the evolution, and I have written one example here, then you can do better forecast. So what it is, this is a discrete time dynamical system. So n is any integer. We take the evolution is given by your system at time n plus 1 is a function of your system at time n. This is for the model. Now we suppose we also have a truth, so the reality, which is not given by exactly your model, but the evolution of the reality or the truth is f at x tn plus 1, tn, plus a certain thing which depend on the time. But usually you don't have access to this because your model is a simplification of the truth. Now, I'm not dealing with the difference between these two things right now. I'm just trying to deal with initial condition. Why? Because if you start with a certain, let's say at time 0, and then you focus for time in the future, everything depends on one initial condition. So if you would like to optimize this initial condition, and so the way we did it is, suppose we have L data, we introduce a function which is the difference between the forecast obtained from an initial condition x after I iterations. So this is a composition of f with itself. And then we use this operator h, which sends the system to the observation. This is the observation operator. And we do the difference between this forecast and the measurement. So we assume that we have the data at the same time. We take the square. In this notation, h has not to be linear. It's just a function of the system. Now, if we want to look for minimum of this, we have to look for the gradient of this function. It should be 0, but if we use an algorithm for computing this gradient, it's not 0, but we can make it close to 0. And last time I just explained if m is 1, and if h is, so m is the dimension of the observation. So if the observation is one-dimensional, and if h is linear, and then it is just a matrix, we can compute this explicitly. And we have the Jacobian matrix here of the I composition of f with itself, evaluated at x. It's a matrix. We take its transpose and we apply it to the vector h. So we end up with this formula, and this is the last thing I have presented last week. And now I have a couple of remarks. But before this, is there any question or remark? And by the way, if you find some mistakes in my notes, of course, let me know. I'm sure the notes contain mistakes. So just let me know. All right, so one remark I already did last time, but maybe I can write it, is if you look carefully at this, this term is made of the observation of the system, but the focus minus the observation. This term contains the observation, while this one is only related to the model. There is no observation. So you can compute it once and use it many times. While this one, you have to update it with observations. So let me list a couple of remarks. One depends on the observation or on the data. Who is independent? Which is good from a computational point of view. This is a first observation. Then this expression, or this one, is usually very complicated. You cannot solve this equation is equal to 0. So you cannot solve this problem most of the time. So as I also mentioned, so this is a remark one. As I already mentioned last week, there are algorithms for doing this. And one, which I'm not going to discuss at least now, but it's quite well known, is called the gradient descent method. So for, let me give a name. For finding X star satisfying this equation star, we can use what is called the gradient descent. And probably, maybe first and second year certainly do not know what it is. Probably third and fourth year have heard about this. But even in the first year, we have an indication about this. If you remember your calculus course 2, when you have a function, and these are the, what is it called? K-level set. We have seen that the gradient is always perpendicular to them. So the gradient at one point is perpendicular to the K-level set. And in fact, this method is based on this fact. You use precisely that the gradient show you the direction of biggest variation of your function. Okay, this is just an indication that this is something we can study. After calculus 2, we can study this. But because it's an algorithm, we cannot expect to find a solution equal to 0, but we can accept a certain approximation of 0, close to 0. So once you have found a X, or X star, which essentially satisfy, then we can use it. And I have made a picture here of this method. So let me explain it. So in yellow, we have the observation. So suppose we are now at n star. I usually use n star. So we are at n star. We have previous data. And we have also been able, because we were studying this system for a long time, also to have some focus. So this focus, the red points were obtained before we had the data. So the red dots are focus done before getting the data. So we had some focus, we have now the data, we are here. So what are we going to use for now for focusing something? We could either use the focus that we have obtained before or our measurement. But we are not sure that this measurement is better because we have some error when we measure it. So what we have done with this method is to minimize. So with this function is precisely taking this distance square. And we are trying to find a new initial condition here. In fact, I should also put a dot here. So a new initial condition here. Oh, no. At this time, this is the initial condition. No matter how we have found it, at this time, this is the initial condition. We started with here, and we have focused these red dots. Now, as I said, I'm here. I want to find the best initial condition for focusing something for the future. So I construct this function trying to minimize. Oh, no, so it's indeed, no, there is indeed 2 points here, sorry. I need also to write it. So now I come back to this initial point, and I'm trying to find a new initial condition, which is YA. I will write a sentence about YA, such that I minimize. Now I have the, yeah. I'm trying to find a new initial condition, which is going to make this distance even smaller, because, yeah, it's misleading. I should not put this first, because if we think about how we do the process. So first, we started with an initial condition. We have focused something that was done 5 minutes ago. Okay. Now, during these 5 minutes, I take the observations. So at this time, we have now a red dot and a yellow dot. And now I'm not sure that if I want to continue, I'm not sure that it's going, which one is going to be the best, and it's probably none of them. So I'm going to find an initial condition here, a new one, such that when I start with this initial condition, it's not represented because it would be misleading, but the trajectory would be even closer. This is why we minimize. So with this initial condition here, I'm looking, so this is what I also called X star. I'm going to have a better approximation of the yellow dots. So this is the X star that I found for X star minus L. And now it ends up here. And now I call this Y A at time N star. And now from this point, which is neither the focus that I had obtained before, nor the data, from this analysis, I'm going to focus, now the yellow points do not exist yet. No, this could exist. Now with this initial condition, I focused something for the future. Okay. And in 5 minutes, I have additional measurements. So I can start again finding a new initial condition for getting something closer here and continuing. So it's a process like this by cycle. I have tried to describe this in the text in my notes. Yeah.
We have some sort of cost function where it is different. The derivative only has one solution. So it means that we can only find one X star. Here we have a term that depends on data, which is term number 1.
Yeah.
So does it make the cost function?
Ah, the cost function. Okay, I see. So say again the last sentence.
So does the term number 1 that depends on data make the gradient have more than one local minimum, multiple local minimum?
I don't think you can answer in general, because look, you have a sum of terms. I don't think you can say that you have only one. No, it's almost arbitrary. So indeed,
like the gradient descent method, for example, we may find
sure. And yeah, you could find different solutions. Then you have to test which one gives you the best initial condition. Yeah. But I don't think that there is a condition on this expression which ensures that you have only one local minimum or one minimum. I don't think so. So let me write a sentence describing this. So when x of n star plus n is focused, so I should denote it. We denote it. Denote by xf for focus at n star plus f. So this, and then n accordingly we have y focused at n star plus l by using the observation operator. But then when data, now the data y n star plus 1 up to y n star plus n are available. So this is what I did before with the picture by adding these yellow points. So we apply the method. We get x star satisfying gradient of L x star to 0, and it about 0, and I should write gradient at time L n star, I guess. So let's check. Okay, when I'm here, I focused. I'm not sure about the time. So let me just follow my notes. Here, yes, probably.
On the picture of the diagram, we wrote x star minus L.
Yes. Star minus.
Also, shouldn't it be like y star rather than x star, like the one right above that? Because like if we choose the initial condition there, we can't really graph x and y in one graph together.
Sure. So, but what we would like to, so if I will represent y, indeed it should be y star, but I haven't introduced y star, which is a projection. So I prefer to keep x star, even if indeed I should not represent it on the same picture. But yeah.
Like about x star, is x star basically at like the initial condition at time n star minus L?
Yes, indeed. It is the one you find the initial condition at this time, you iterate it L times, and then you use it for the next step. Yes.
So the initial condition changes is actually not the initial condition for now. It's the initial condition for one period ago.
Yeah, but for this white curve, this is why I call the white curve. I made this white curve because you use this evolution only for the next step. You have a kind of delay. I guess it's also possible to do it backward, but now I prefer to work forward.
But so after that one period, we just forget that y star.
Yeah, y star is never used. It's just used for the computation. But it's because when you draw y star, you already have the data. So it's not visible on this picture.
After the period done, we just forget y star ever existed, but we just say
we just keep this point.
Yes.
This point is the important one. The other one are just fake because you have been able to play with both the data and the previous focus.
Okay, thank you.
So we get x star. So let me not write any time, satisfying this for the next cycle. If you think about the picture, it's understandable for the next slide. And we should call X analysis of n star plus L. Yes. And Y analysis, which is H of XA. So please check the time. I'm not completely sure about the time in the text, but the picture should be correct. So this A is for analysis. Just check. It's not easy. A few more remarks. So this was 1, 2, 3. I have done 2 simplifications. One was to take H1, to take Y one-dimensional. So it was M is equal to 1. And the other one was to take H linear. We can drop these 2 assumptions. So, and the first one is if M is bigger than 1, there is no problem, because look at the function L. If you look at L of X, it's a sum of square. And if you have a vector, the norm of the vector square is again a sum of the square of each component. So if M is equal to 1, we can just add different component square, or add the norm square of Y at n star minus L plus I minus Y at n star. Now it's a vector, but we take the norm square. So it means you take the sum of the component square. So it doesn't change anything. Now what about if? So it means no problem. It's maybe more difficult to write it, but it doesn't change the approach. Now if H is not linear, the final formula I have introduced cannot be used. But you can check, it's also doable. We can also do it. So for H is not linear, one can still compute gradient of L. So what is the difference? If you look at the formula I have used, I was able to factor H because it's linear. Now, instead of having gradient of F composed with I, you have to replace this by gradient of H of F I at X. You have to consider one more function, which is probably more complicated, but still it's possible. There is no obstruction. One can still compute by using so you use this expression instead of this one. So it's yeah, one is, so this is the observation and this is the focus. Yeah. Sure, thank you. And one more remark or 2 more remarks, but they are very short. So far, we have not considered the model error, which means I have indeed tried to minimize this, but if the model is not perfect, you cannot expect that these two things are always close. So you need to take into account, and it's not in the framework I have presented, but you have to take model error. So if we have, maybe we don't know the function g I have introduced, but maybe we have a certain kind of information about this model error. It's not easy to get something, but if we have an information about how close our model is to the truth, we can add this information at this level. So I hope we can do it later. We have to take this model error into account. And the number 6, and this justifies the next chapter, is we have no probability so far. We are just saying we focus something, but how confident we are in our focus. There is no information about this. So now we need to add an information about how confident we are for the forecast. And indeed, if you think about the weather forecast, they give you an information, and this information depends on the day. One-day forecast have a certain probability. The 10-day forecast has another probability. There is no information like this. So we have to add an information about how confident we are for the forecast. And this information can depend on time. So when you speak about confidence, it's about probability. So we have to do something about probability. Right, so this is the end of the first chapter. We have already seen quite many things. Still, there are many things that we have omitted, and we will come back to them. Any question or remark? So probability. I will try to make this second chapter as short as possible. In the book I'm now using, it's about 2/3 of the book about mathematical background. Of course, I don't want to spend 2/3 of my time on the mathematical background, but I need to introduce a few things. So if you have attended the course on probability 2 semesters ago, it's nice, but I will recall and do something very much related. Mathematical. So I hope to do it within 2 or maximum 3 weeks, this chapter. I hope 2 weeks. That one, it's about probability. Maybe 3 weeks. And random variables. And if you don't know what to do during the Golden Week, I have a suggestion. I have about 100 pages written like this about probability on my website. So if you don't know what to do, you can just open these 100 pages and have a look. It would be useful. So what is the aim? Is to quantify non-predictable experiment. So if you can predict it exactly, you don't need to quantify, but here are non-exactly predictable experiments. But we need some tools to describe this, And we need some definitions for dealing with this. I've decided to present a very general approach. Why? Because I observe that it comes back and forth many times in different subjects. So I try to give a framework which can be used in another framework. And it's even more general than the course I gave 2 semesters ago. So let me start with a measurable space, which I haven't introduced before. In fact, it's very simple. Is a set, which I'm going to call lambda, capital lambda. This is capital lambda. And a family subset lambda satisfying 3 conditions. So if you think about a picture, you have a set capital lambda and you have subset. You have subset. So your family of subset, I should give a name to this family. This family, I will call it curly E. The family E of subset satisfying some conditions. If A is an element of E, it's a subset belonging to this family, then its complement, and I will denote it by AC for complement. It is the initial set minus A is also in E. So whenever you have one set, you have the complement. So if you take a countable family, so you take a countable family of subset, so countable family inside E, then the union is also inside. Union of AJ is also inside E. Be careful, the family is inside E, but one subset is inside E. So when you take a family with or without intersection, doesn't matter, the union is also inside. And the third one is if you still have a countable family, the intersection on J, AJ also belongs to it. So this is what is called a measurable set. I will give some examples later, but this is quite natural. A set with subset, you choose a certain family of subset, but this subset, this family has to be stable under complement. So maybe I can just write the name of this condition. So the first condition is stability under complement. So this is stability of E under complement for the first one. This is stability about countable union. And stability on countable intersection. Countable because, if you have never heard about this, this countable is related to n. You can count them. Even if it is, it can be very long, it can be infinity, but you can count them. The difference is with, if you take the set of real numbers, you cannot count them. You don't know how many there are. This is countable with this n. Now a small exercise. And let me give an exercise. If the full set, lambda belong to E. So if the entire set belongs to E, then 1 plus 2, the first two conditions imply the third one. So you don't need the third one if the entire set belongs to. You can check how to do it. This is not so difficult because you can consider the complement, and there is a relation between intersection and union if you think about the complement. Oh yeah, somebody asked me about some exercise. So far, it's very difficult to give you one reference book because I'm taking some information from different books. I hope I cannot later on give you more exercise or more precise references where you can find some exercise. But I have already written 1 or 2 last week, 1 now, and I'm going to write a few more today. Just for another word I need to introduce. This pair is also called sigma algebra. Maybe you will find this word somewhere. This is sigma, but this is just a name. Okay, so now we know what is a measurable space, and I can define the main object of probability, which is a probability space. So probability space is made of 3 objects. So it contains a set omega, a family F, and this. Let me just give the name. This is capital omega. We already know the first 2 ingredients. The first 2 ingredients is a measurable space. So it means this is a set, and this is a family of subset. So I took this part outside of the definition because I can use it for different purposes. So these 2 things are exactly what I have introduced there. So a probability space, it's 3 things with this capital omega on F, a measurable space. Together with this information, with omega belonging to this family, which means because of this exercise, the family of subset is stable under complement and countable union, and for free you have countable intersection because the big set omega belongs to this family. So it's exactly the framework of this exercise. And what is P? Let me do the picture again. What is P? P, it's a function defined on F, with value in 0, 1. It's called a probability measure. But how you should think about this, it's a way to give a weight. You want to know what is the weight of each set. You want to measure either the size or the weight of each set. So it's a probability measure satisfying it satisfies P of the entire set is 1. The weight of the entire set is 1. Measure of the entire set. P of the 0 set. This is the empty set. Empty set. By the way, why this empty set has to be in F? Because of this property of complement. If omega is inside F, its complement, what is missing, has also to be in the family. So the complement has to be in the family. But the weight is 0. And we have one more property, P of a union, a countable union. Probability of a countable union is the sum of each probability, but with one condition. If intersection, if AJ intersection with AK is equal to empty set for any J different. So in my picture, I cannot take arbitrary sets. I need to take only the 3 yellow one. These 3 have no intersection. So if I take the weight or the probability of this union, the union of the 3 yellow sets, it is a sum of the individual probability. That's a probability space. So it's not so difficult. You have one set, one family of subsets, which has it respects some properties, and one way to measure the size or the weight of each of them. And just for the definition still, omega is called event space. It's just a name. Any point in omega is called an elementary event. And A belonging to omega is called just an event. These are just the names of this set. So if we think already about the applications later, most of the time, we will have no information about this in the applications. This is a very, very complicated set. Omega is going to be complicated because it's going to describe all possibilities that a system can take. So very often we have no access to this, but from the theoretical point of view, it's necessary to introduce it. And now we are going to build different objects on this set or on this probability space, and these will be accessible. And if you throw a die, if you play with a die, you don't know there is an equation of evolution which should tell you that you get this result. But there are too many uncertainties and too many things. You don't play with your phone, please. There are too many things that you cannot control, that it's impossible to describe all possible trajectories. But this omega would describe all possible trajectories, but we don't have access to this. You know, if I would start playing with my phone now.
I was looking for the old lecture notes on what omega is.
Okay, you can look later. And it's not exactly the same. I haven't introduced measurable space last time, and the difference is going to appear right now. So as I said, omega is usually not accessible, but we are going to define functions on omega. So omega is usually not accessible. Consider functions on it. And this is the next definition. What is a function on omega? A random variable, which I'm going to denote by capital X. Random variable X is a function. Okay, let me anticipate. Usually I shouldn't do it. It's going to be a function from omega to a set lambda, but I haven't introduced these two, so I'm going in this sentence. It's a function from omega to a capital lambda with so this omega is part of this probability space. And who is this capital lambda? So 2 semesters ago, I used just a set of real numbers. But this is not the best thing. So this lambda is a measurable set. Or measurable space. And let me just already mention, for example, so one example, and this is a traditional example, is just a set of real numbers. I will just explain this in a second. Satisfying, so with blah, 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 we have a condition satisfying this. So I know it's quite complicated and abstract, but usually it's better to give the abstract the full picture first, and then we can deduce some simpler situation. But if I give you a simpler situation first, then I have to cheat. And in the book I'm using, they are cheating, and I don't want to cheat with you. And I will show you why later. So what is this definition? Again, it's a function from, let's say you have the set omega, you have the set capital lambda, you have subsets in this one, you have subsets in this one. These are they belong to capital F. Here they belong to E. And the only condition is that, what is this notation? This notation is the set of omega, small omega belonging to capital omega such that X of omega is inside A. Look, take an A here. This is one A. Look at, we have this function capital X. Look at the set here, which is sent on this one.
Will that be A in lambda, not in omega? I was very confused about that.
No, A is, no, A is,
A is in omega.
no. A is inside lambda, but it's one element of the family. This belongs, no, this is correct.
Like the right one. And A inside omega is called an event.
Wait, you are here.
No, I'm like, I was very confused about that one because you said A inside omega, but now it's A inside omega.
Okay, because I have used the letter A for all elements, either in omega or in lambda. You're right. A is just one example of an element in the family. Okay, sorry. If I start to change the letter each time, it's even more confusing. So let's check again. This x minus 1 of A. So what it is a set of small lambda, small omega in this set, which are sent on A by capital X. So this set must belong to F whenever you take A in E. This is this condition. Now, well, first, is there any question about this? What is the, or maybe I do one example? Yeah, I can develop this example. So I need to say something about this. Why? Because it's always made of two things. One set on a family of subset. So if I give you this set is R, I need to say something about E. What is this set of subset here? So I need to add one information, even in the special case of R. So two examples now. And I will, with the second example, I will tell you why I have introduced this slightly more general framework. For example, the first one is this capital lambda. You just take n, and you can even take n equal to 1 or 2, any number. But the traditional example is n is equal to 1. Let me give a name to this condition. This is a condition star. This condition, I call it the condition star because it's really the important condition. How do you check this condition? So I give you the key point on star is satisfied if, so I do it in the n-dimensional case. If, I'm sorry, I know it's complicated, but like in calculus 2, when you have a function to Rn, I already mentioned this last time, it's like n functions. So if you have a function x from this to Rn, it's like n functions, right? A vector, a function taking a value in Rn is like n function. So it's satisfied if x, this random variable, you can look at it as n components, verifies set of omega in this is something which is more familiar if you have already seen random variables. So what it is, again, x is a family of n functions. So I consider this n function, and this condition is a set of omega in capital Omega such that each component is smaller than a certain number for all x1 to xn belonging to Rn. This is a traditional way to look at one random variable. Think about one dimension. If capital N is 1, you only have one condition. You want the set of omega such that x of omega is smaller than any number to be inside F. Why you need this condition? Because later on this corresponds to measurements, and you want to have a way to measure if a quantity is smaller than a given x. However, these two things are not exactly the same. So let me just now introduce what is here. I don't know if you have already heard about this. I need to give you a set of subset of R. This is called the Borel sets, the set of, or the Borel algebra. Here, this is called sigma B. It's called the Borel algebra. This is just the name of one person, the Borel algebra. And what is this Borel algebra? You take all intervals and you generate other sets by taking countable union, uncountable intersections, and complement. So you take any number of intervals and you make intersection or union or complement. So you generate a huge family of sets, and this family of sets has exactly the property you need. It has to be stable on the complement, countable intersection, and countable union. So this Borel algebra is generated by intervals with countable unions, intersections, and complements. So this is what is missing here. But fortunately, the good point is you don't have to check that for any such set, this condition is satisfied. This would be horrible. It turns out that if you, in fact, what you are checking here, you are checking it only for half intervals or half lines. You are checking it for all points. If you think about x, all values smaller than xj are half lines. It's from -infinity to xj. So you are using this condition only on some very special interval, and this is sufficient. All right. So this is a usual framework for random variables. If n is 1, this is just one random variable. If n is different from 1, you have a family of n random variables. And now what is the second situation? Okay, during this golden week, you can also just read again your notes because it's quite dense. The second example is take lambda, this is a finite set. So you take n dots like this. That's it. A finite set with n elements. But again, I need to tell you who is the set of subset. And here it's canonical. You take all of them. So you take the sets containing only one element, then you take the one containing two elements. Okay, there is a canonical way name, I will write it. And the one containing three elements, and the one containing four elements, and the one containing five elements. So, and take, so this set E, this is called the power set of lambda. And what is the power set of lambda? It means the set of all subsets of lambda. Do you know how many such subsets do we have? We can count them. It's a finite number. Two power n. We have 2 power n. Why? Oh. Because either take one set and either one point belong to it or not. You have always two choices. You have 2 power n elements in the power set. Example, why this is useful. You know, if you play with a coin, you are going to just consider heads or tails. Just two choices. If you play with a die, you are going to consider the set of 1, 2, 3, 6. And that's it. With what I introduced 2 semesters ago, you need to do one identification of this set with a subset of R, but it's not necessary. With this definition of measurable set, a random variable from omega to lambda can just take values in this set or in this set of 6 faces of a die. That's it. So it's slightly more general and slightly more natural to have all these examples in the initial definition. So random variable takes it's a function from omega to either Rn, I mean the main 2 examples are Rn, or a finite set, but it can be also more general. And I've seen that even in machine learning now they use this kind of language. Okay, so this is why I decided to give you the general definition. Yeah, this part of the lecture has not really any relation with what we did just before, but the relation will come later. Okay, so we have random variable now. So when x is from, when I write this, but let me just mean that here we have a probability space. And here, this one is part of a measurable space. But the function is really taking from this space to this one, from this set to this one. Okay, so when we have this, is a random variable. We can define the following map. Ux of A Oh, no, mu x. It's mu. It's going to be a function from e to 0, 1. Remember, p was a function from f to 0, 1. But I told you elements of omega are usually not accessible. On the other hand, this is much better. For example, if it is Rn or if it is this finite set. So we define the map from this set E with value in Rn by mu x of A. You can almost guess the definition. No, it's no more on the blackboard, but remember, we had this set omega, this set lambda, and the condition was whenever you take a set here, it has a pre-image. So x is going in this direction, but the pre-image, the x minus 1 of A, sorry for the letter A, the pre-image of A was an element of F. So the natural definition is you measure the weight of x minus 1 of A. And let me give you a different notation. This is the weight of the set of omega. So that x of omega is inside A. And it's also written, these are different notations. It's also written P of x belonging to A. I don't really like the last notation. This is just a notation, but it is commonly used. It's just a notation. The most explicit one is the second line or the first one. But it's well defined because as we have seen, this element here or this one, it belongs to F, and P takes the weight or takes the size of any element of F and give a number between 0 and 1. So we can define it. And now this is much better, or much better than P, because it's defined on this space, and not on F. And maybe you heard about this word. So this is called mu x is the induced probability measure. Meaning that it's induced probability. Here, induced means it's coming from X. The induced probability measure and is called the law. Oh, we have nobody in law. The law of X. This is the word, the law of X. And later we are going to use Gaussian, and these are also some laws, Gaussians or other probability distribution. The law of X, and we write X is related to its law. So what is the difference again? We had a probability space. X is a function from the probability space to omega. No, sorry, from X to lambda. And now this is a function defined on the subset of lambda with value in 0, 1. So we have, maybe we can try to make a picture. I didn't think about it. Let's try to make a picture. We have this complicated set here. Now we have a random variable x going to a simpler set here. I have A, its prime edge is this one. So this one is x minus 1 of A. Now, P is a way to measure. This is P of x minus 1 of A. But this is complicated. So from here, I introduce this mu x. And this is this belongs to 0, 1. Yeah, this is a nice picture. You have this complicated space. One random variable is a function on this complicated space with value in lambda. Now, P is a way to measure the size of this. So we define how the measure of this set A by this come back and then P, but we define it directly here. And this is simpler. You know, 1 hour 30 is not long enough. We should have more time. So let me propose to have 2 hours. No, I know I would be happy, but it's not fair. Okay, now I'm even going to do one more step. Now I'm going to go from here to another place with a certain f. And this is where people are cheating. So I'm going to introduce one more thing. This is a complicated letter. It is a capital Xi. This should be in the middle. Okay, let me just say most of the time people are thinking about this as R. And we are going to let me just, I'm very vague, so just don't copy. This is going to use for expectation. We want to compute some expectation. So this is a space used for expectation. So people use this with value in R, and then they cheat because they compute the expectation of a matrix. Matrix, sorry, which letter? B. This is a matrix, n by n. But if you have defined an expectation as a real, don't write because it's too vague. But if you define an expectation on real number, then you're not allowed to use it on matrices. I mean, this is not coherent. I'm defining something, but I use it for another purpose. So I prefer to introduce something first more abstract, but then in application, we will see that it is often R, but sometimes we have to deal with matrices. When we compute a covariance, it's going to be a matrix. So let's take it abstractly, and we will understand later. Or we will have some example later. So I'm going to use a new space. And because I have introduced, it's going to be simply a measurable space, which means a set and a family of subsets. Now we are familiar with this. Okay. So now we consider F. We consider F. which is from this to this set xi or xi, which is measurable. Now I haven't introduced this explicitly, but you know already what it is. What means a measurable function? Can you guess? I mean, this set has some subset. This one has also some subset. So what means measurable? We have already done it before. It means whenever you take one here, there exists a set in this family which is sent here. So it means measurable means f minus 1 of A, sorry, belong to this space. So this is part of this, and this is part of the G. So this f minus 1 of a set here, this is A, belong to this family for any A inside the family G. And this is exactly what we have already done. We did it at this level. So now I can say this is measurable because this is the condition we have imposed. I just do the same, measurable. Before I didn't mention this word, I just mentioned the condition, but now it's even simpler just to say this word because it means exactly what I have in mind. Expectation. When you measure something or when you do many experiments, you want an expectation or kind of mean value. Any measurable f from this space lambda to I. But this one is part of a measurable space like this, and this one is part of a measurable space like this. Measurable means if you take any set in this family, it's a set in this family. Expectation. F, this is a keyword, the expectation of f, of fx is defined. Expectation of fx, now I need to give a formula. Integral okay. Yes. Say it again.
Is x the random variable?
Sure. Capital X is always a random variable. So it is exactly in this picture. We have capital X, one random variable from this space to this one. And then we have f from here to here. So the f of x is a function of this random variable. And I'm writing its expectation is this, but this formula should not be understandable because you have never seen this. Precisely, I need to say, what is this? The domain of this integral is over, yes, it's over this capital lambda. This is yes. So let me keep this picture for a second. You know, you have seen only Riemann integral. Anybody has seen Lebesgue integrals? Okay, so it's, in a sense, this is a Lebesgue integral. So what is it? It's good to introduce this. This is a limit of a finite sum f of yj mu x of okay. So I'm not sure it helps, but let's look, and we are going to do a picture of this. You know, let me just first do a picture of a Riemann integral of one variable. When you do a Riemann integral of a function on an let me do it. Take a function like this. Oh, not Take a function like this. When you do a Riemann integral, usually you subdivide this interval and you take something like this, 1 point, you compute your function at this point, and so on. I mean, I don't want to repeat everything, but this is a typical picture for a Riemann integral. Now what? It's not completely true, but what is a Lebesgue integral? This picture is not always good because on this picture you can see this rectangle here is not very good because the function is changing a lot on this interval. While here it's already almost constant, you could just use one bigger interval. So this partition of the x-axis is not always the best thing you can do. The idea with a Lebesgue integral, so let me try to make a function similar, is to do a partition of the y-axis. You do a partition of the y-axis, and you look at you are going to partition the x-axis according to your partition of the vertical axis. And this is, look at this formula. So let me do it. Okay, it's a little bit, okay, it's complicated, but again, I'm doing a partition of the vertical axis. It gives me some interval where the function takes value inside an interval, right? And then what I do, I take f of y is on this. This is a typical f of yj. One number inside this interval, and it is multiplied by the size of the preimage. So this is the size here. So this measure of the preimage of an interval. This interval would be aj, and you look at the measure of f minus 1 of aj, and you do the sum. So you end up with the same, at least for nice function, you end up with the same quantity in the limit. But in fact, for different reasons, the Lebesgue integral allows you to consider more general functions than Riemann integral. So all Riemann integrable functions are Lebesgue integrable, but the converse is not true. And so let's check that it's well defined. This expression is well defined. What is this? Aj is a partition of this space. So you have a partition of this. Yeah, you take them disjoint. Sorry, my picture is not good. So if I want to draw a kind of partition which do not overlap, I should do something like this maybe. I take a partition of this. I look at the preimage here. This is going to be a partition like this. I measure the size of this, and I multiply by the value of f at one point. So the y. Let's take this one. So this is AJ, this one is AJ, this one is F minus 1. Oh, no, sorry. No, I'm doing a mistake, sorry. I should do it at the next step. Sorry, the picture is here. I did it at the wrong place. I have a partition here. And then it makes a preimage. Oh, this one also exists, but it takes a partition here at this level. I take a AJ, I take F minus 1 of AJ. Then in this region, I have a YJ, and we have a F of YJ. But now the size of this is computed by the previous definition. So in fact, I have also some, I don't need to write it here, but the size of this is the PG, the probability of the corresponding set here. So in fact, you have the three pictures. So you need to check, I mean, it's a full theory. I cannot present everything, but first you need to check that this is well defined. This is clear, but then you need to check that taking a limit is meaningful. And this limit with finite and finite partition is what you denoted by this. So your question, is it correct? This is just a notation, but indeed it corresponds to an integral over this space.
So we take the limit Sj goes to infinity and we take like very small aj.
Yes. Yeah, like for Riemann. But we take the difference between Lebesgue and Riemann is that for Lebesgue, you do the partition over the image and not over the initial spacings. Is there any question for this? I'm trying to give you a lot of information. I guess it's the first time you see Lebesgue integral. So, okay. But if you have this picture in mind, the difference between Riemann and Lebesgue is essentially this one. It's already good. Do you give me 5 more minutes? Just to give you an example. And now, okay, let me do the example. Keep in mind this notation. So again, like for Riemann integral, this is just a notation, but it's a limit of a certain procedure. So example. Oh, it's a definition, but it's in fact an example. There exist two special types. Of random variables. So I'm going to give you, today I give you just one, but when this space is Rn, so I gave you a general definition with X, a random variable from the probability space to a certain space, capital lambda. And I said most of the time it's either Rn or a finite set. Now I'm going to give a special case when it's Rn. So when this set is Rn, and the first definition, and this is also an example, a random variable X from omega to Rn is absolutely continuous. This is the most common case, is absolutely continuous. If this integral f of x d mu x dx, again, this is just a notation. But if this integral, this number is given by a regular integral f of x I x x. I want to keep this general picture. And what is this pi x? Pi x from Rn to 0 infinity, satisfying integral of pi x of x dx. It's a usual integral on Rn is 1. And how is it called? How is this pi x called? It's a the probability density function. It's pi x. It's probability density. So I'm saying we call a random variable absolutely continuous if this complicated expression is given by a regular integral. I would say regular, I'm cheating, regular, because officially it should be a Lebesgue integral and not a Riemann integral. But most of the time you don't see the difference. So regular integral. So it's the integral of a function with multiplied by a certain density or probability density function dx. So this is what we are familiar with. So in this case, when we have such a function satisfying its integral is 1, it's called the density function, PDF, probability density function. And we write x is related to the law pi x or not. So I use this notation instead of pi x dx. In fact, if you carefully think about it, the measure, I mentioned already that x is related to this measure mu. Now, in case it's absolutely continuous, I just say that random variable x follows a law given by its density. But in fact, I should write the density times the Lebesgue measure. This is the small dx is a Lebesgue measure. but this is again just a notation. Okay. And the other case, the second one, is a discrete random variable. Last semester, when I spoke about it, I started with discrete valued random variable, and then I continue with continuous random variable or absolutely continuous random variable. Now I'm just putting everything in the same framework. Two special cases are this absolutely continuous case and the discrete case. Okay, I know it was hard. It was also hard for me to prepare it. Again, I introduced this complicated space. If you look at this definition, you can just think about R. It takes value in R. But sometimes we are going to compute some expectation of matrices. Then it's, I mean, I'm not saying what is exactly this object. It's an element in this space. It can be a real number, it can be a matrix, it can be a vector. Sometimes we will compute the expectation of a vector. So I need to have this flexibility. So next week we have no lecture, unfortunately. But I encourage you to read your notes or to read my notes on the website until page 25 or 24, 25. I wanted to do a little bit more today, but it's fine. But I will just start from this point. So please try to keep this in mind for next time. We will use this language later on for measuring the probability of some forecast. Any question or remark? It's clear.